Welcome back to CS520. In this session I'm going to talk about the Intel IA-32 architecture. In other words, the architecture of the machine that we use for our programming assignments, agate. The main goal here is to understand how function calls are supported on the Intel machine. So I'm not going to go through all the many instructions point by point. Rather, we're going to focus on how the machine supports recursive function calls and how does it handle return addresses and return values and parameters and local variables. We're really trying to understand what we need to know in order to be able to implement things like garbage collectors, thread libraries, and so forth. If you want to learn all the details about particular instructions, then you need to consult the Intel manuals. One word of caution, the Intel manuals assume the Intel assembler, and we'll be using the Linux assembler. And the big difference there is the order of the operands is swapped to meet the Linux conventions. So just keep that in mind if you do take a look at the Intel manuals, which are linked off of the course website. So what's the big picture on this machine? Well, the IA-32, as the 32 would imply, it's a commonly called a 32-bit machine, which is, you have to dig a little deeper to see what that means, but in this case it means 32-bit addresses and 32-bit integer registers. Like all modern machines, the memory is byte-oriented, however. Let's go back and take a look at those 32-bit integer registers. By integer registers, I mean commonly hold integer values or addresses. There's 6 general purpose registers divided into 2 groups depending on responsibility for who saves and restores them, either the caller or the callee, and we'll talk more about this in a moment. But there's basically 6 basic general purpose registers with those names. And then there's 3 particular registers used to support the execution of the machine and function calls. So there's a stack pointer that points to the top of the stack. There's a frame pointer that points to the topmost frame on the stack, and there's an instruction pointer which often would be referred to as the program counter for the machine. By the way, these E's on here are all stand for the word extended. Again, the Intel machine is probably the most successful computer architecture ever. And one of the big reasons for its success was it was always upward compatible. So this machine used to be a 16-bit machine, and it was extended to 32 bits, and all these registers names had the E added to indicate that they were 32-bit registers. However, the 16-bit register, inside the 32 bits is still available. You can refer to it, for instance, for AX. You can refer to the 16-bit portion of that extended register. So again, you'll see a lot of that as you look at the machine, that it's been designed to be an upgrade from a 16-bit architecture. One note about floating point is there's actually floating point registers on the machine. They're 80 bits. They're not 32-bit for IEEE single. They're not 64-bit for IEEE double. Rather, they are 80-bit with Intel's own proprietary format. We're not going to do a lot with floating point computation in the course, but one thing you should just put in the back of your mind, that Intel doesn't represent values in the registers, floating point values in registers using the standard formats. Rather, it stores values in this proprietary Intel format, and values are converted to the standard formats when you write to memory, and they're converted from the standard format into the Intel format when you load a value from memory. So this can sometimes give you slightly different results than you might expect if you thought all the computations were being done in IEEE formats. What happens is inside the CPU, they're not in an IEEE format. So just put that in the back of your mind. It's if you ever end up doing floating point computation on the Intel hardware. Just a note about terminology here. On this machine, we'll talk about a byte. That's not unusual. That's an 8-bit value. We'll talk about a word, which on this machine is 16 bits, again showing its sort of its heritage as a 16-bit machine. And then a long on this machine is 32 bits. And we'll be seeing, single character designations of this when we look at individual instructions, right? B for byte, W for word, and L for long. Okay, one of our key concerns is about the stack. So on this machine, the stack grows from high addresses down towards low addresses. And as I said a moment ago, the ESP register always points to the top of the stack. So if you look at a program running in a Linux machine, this is typically the picture where at the top of the diagram here I'm showing low addresses. You'll find the code followed by the static global data, followed by the dynamically allocated malloc data, and that's dynamically growing down towards higher addresses. And then up at a higher address you'll see the stack, and it's growing in the reverse direction. It's going towards lower addresses, and of course the stack pointer is pointing to the current top of the stack. So it's important to remember the stack is growing from high addresses down towards low addresses. I mentioned that there's a register called the frame pointer. What is this all about? Well, stack contains a series of frames, and there's one frame for each active function call, and the frame contains the necessary information about that particular active function call. So it's the return address. Where am I going to go when this function returns? What's the PC value going to be when I return? I may have saved registers because the caller might have been using the registers, and I need to save those contents and restore them before I return back to the caller. I'll have local variables that I need to represent. Those will be on the stack. I'll have parameters that are being passed to this particular invocation of the function, and the function may need additional temporary spaces, which can be allocated on the stack. And again, as I mentioned, the EBP register points to the top frame on the stack. So let's take a look at a more detailed picture of the stack then. This is really the critical thing you need to know when we do some programming assignments at this level. Again, high address towards the bottom of this diagram, low addresses up here towards the top. I'll try to be consistent in the course and draw them that way, but sometimes I might forget, so you'd have to look, and I'll try to always label them. So high addresses down here, the stack is growing this way, okay? So below us on the stack is all the other frames for all the other functions that are currently alive. So somewhere down there at the bottom is the main, the frame for main, and then if main called something, and that function called something else, and then finally the currently active function is called, we'll see the frame for the currently active function at the top here, and we can break it down into its components. The stack pointer, as always, is going to point to the top of the stack, the top item on the stack. The frame pointer is typically going to point into what I think of as the middle of the frame, and we'll start talking about words as offsets from where the frame pointer points. So if we look at what the frame pointer points to exactly, at a 0 offset, it's the old frame pointer. In essence, there's a linked list that goes back and chains together all the frame pointers. Right? The current EBP points to the top frame points to the next frame, that frame points to the following frame, all the way back down until the main function. And in fact, the main function points to another frame, I believe, underneath that, which is sort of a stub that the operating system introduces, which calls your main function. But there's in effect a linked list of all these saved frame pointer registers back. If we look at what's below that, or depending on your point of view, what's above that, at a higher offset off the frame pointer, we'll see the old instruction pointer. So this is the return address. This is where this function is going to return to when it returns. It's going to reset the PC to be, or the instruction pointer in Intel talk, it's going to reset it from this value saved on the stack. At even higher positive offsets than from the frame pointer are the parameters that are passed to us. It turns out on this machine, the caller pushes the parameters onto the stack prior to doing the call instruction. So the caller will have pushed the parameters onto the stack. Again, the stack is growing this way, so parameters will be pushed typically. Well, they have to be, I guess they're pushed in reverse order so that the parameters are in increasing memory order, right? If this is the first parameter would be here, the second one would be here, say, the third one would be here, the fourth one would be here, right? The caller would have to push the fourth one first, then the third one, then the second, then the first. But the nice factor of that is from the called routine's point of view, that vector of parameters is in increasing memory order. The first one's at a lower address, the second one's at the next higher, the third one's at the next higher address, and the fourth one's at the highest address. And the parameters are indexed off of the frame pointer. The first parameter is 8 off the frame pointer. As we'll see in the program, in the assembly language program we're going to look at in a minute, is you express this kind of thing in Intel assembler like that, right? I'm saying the the parentheses really indicate in direction. So I'm looking at what the frame pointer points to, but adjusted by 8. Why 8? Well, everything is in terms of 32 bits here, so that's 4 bytes. So each location on the stack here is 4 bytes. So to go from the old frame pointer to the old instruction pointer is an offset of 4. Then to go skip over another word, it's go to 8. So in fact, the parameters are indexed at 8 off the frame pointer. You can refer to the first parameter that way. The second one would be 12. The third one would be 16. The fourth one would be at 20 off the frame pointer. Okay. Well, negative offsets from the frame pointer are used to get at local variables. So the called routine would allocate a chunk of memory for local variables by simply moving the stack pointer up. It's really down in memory. Subtract from the stack pointer the number of bytes it wants to allocate for locals, and then locals would be allocated with negative offsets off of the frame pointer, right? This is -4 off the frame pointer. The next one would be -8, and so on. And likewise, temporaries would also potentially be up here on the top of the stack. Okay, so that's the big picture for what a frame looks like and how you locate the parameters, the return address, the old frame pointer, local variables. What about the return value? Well, return values are returned in a particular register, the EAX register. Again, this is a set of conventions. The hardware actually doesn't mandate much of this. This is just a set of software conventions that when we write assembly language code by hand, or compilers generate assembly language code automatically from C or C++ or whatever, by convention they're going to put integer function return values in EAX. That way my code can that I wrote by hand can interoperate with code generated by the C compiler. So a lot of this stuff is just convention. Every machine has its own conventions. I mentioned before the need to save and restore registers. Let's take a closer look at that. Again, this is part of the conventions. On Intel, the convention is that calling functions are responsible for saving and restoring these 3 registers, EAX, ECX, and EDX. So if the calling function needs the original values that were there before the call, if it needs those after the call, then the calling function is responsible for saving those onto the stack before the call and restoring them after the return. And the other 3 registers, EBX, ESI, and EDI, are the opposite. The called function is responsible for saving and restoring those 3 registers if it uses them. So if the called function is going to use EBX, it's going to have to save EBX into its frame before, I'm sorry, right upon entry, and then restore EBX right before the return. So we talk about caller saved, and then this is callee saved. And again, this is just a convention. But again, if we conform to the conventions, then we know our code can be linked in and used with code somebody else wrote, or code that's compiled by the C compiler or the standard C library or anything else. So it's very important that when you're generating assembly code either by hand or from a compiler, that you follow the conventions. All right, now I'm going to use an example program to try to illustrate how the machine works and show you some typical instructions and so forth. And this code is available on Agate in the public area. So you want to go pick that up. In fact, you might want to stop the video now and go get a copy of it so you can have it to mark up as I walk through it. One thing to note is that assembly code can be compiled just using GCC. The GCC tool, again, is a script that looks at the file extension. In this case, we call assembly language.s. We use the file extension of s. So I can compile this program in order to run it by just doing GCC fact.s, call the executable fact, and it's just a simple implementation of the factorial function, and in fact it's hard-coded to compute factorial of 10. And I'm going to walk through this, first the main function, then we'll take a look at the factorial function itself. Okay. So first thing you'll note when you look at the assembly language code is there's comments. The hash mark here on a line indicates that everything to the right of the line will be a comment. And if you end up programming at this assembly language level, you're going to need lots of comments because the code is, becomes fairly detailed, and you need to explain what's going on. Another thing is I find blank lines, so often we'll use blank lines to space things out into blocks to try to make the code more readable. These lines that have things that starts with dots, those are directives. Those are not instructions. So we've seen the notion of a directive in the VM520 machine. We have the same thing in real machines. This first directive here, .text, indicates that what follows are instructions. For some reason, the Unix world uses the term text to refer to code. That's just a historic thing. But basically, the assembler here that processes these files will either assemble instructions into one segment in memory, or as we'll see later, data. If you look down here, here's another directive called .data. What that's saying is it's telling the machine or the assembler to assemble what follows into the data section. So it's basically allowing you to assemble two different streams at once, either instructions or data, because it's important typically to keep the instructions and data separate. So the assembler allows you to be building two different streams, one for instructions and one for data, and then it'll put the two streams together into the final object code file. So I can just toggle back and forth between text and data by either saying .text or .data. In this case, I'm going to start with some instructions, so I'm starting with .text. The dotted line 4 says that I want the next thing placed into the object code to be on a clean 4-byte boundary. This is just for efficiency. Again, it's a byte-oriented memory, but the memory system will work better if you're fetching 4-byte chunks, integers, from nice, clean, even addresses, addresses that are divisible evenly by 4. So that's all we're saying. We're telling the assembler to waste some space if necessary, but get the next thing that's going to be assembled on a nice, clean 4-byte boundary. It's not actually necessary for correctness, but it's necessary for good performance, and this is just boilerplate code that you put at the top of functions, basically. The .global main is telling the assembler that I want this symbol to be visible to the linker. So I'm sort of by default, assembly language symbols are going to be hidden and only be internal. not be known to the linker. So I have to explicitly tell the assembler that I want the label to be put out there and be made visible to the linker. So the reverse of C. If you remember, in C I use static to hide things, and by default everything is visible. But in assembly language, at least in the Intel assembler, I need to explicitly say what I want to be made visible to the outside via the linker. So I'm defining a main here because all Linux programs have to have a label called main, because that's where execution will start, and I need to make that globally accessible. And that label is what we see next, a label definition. Again, my programming style is to put these labels on lines by themselves because I think it makes it more readable, but it's not necessary actually. Okay, the next two lines are actual instructions, and they are, again, boilerplate code that is always performed by all good Intel functions upon entry. And what they're doing is they're starting to set up the frame. And let me start drawing a picture here of the stack. So again, if we have the stack, if we think about the stack being low memory up here, high memory down here, then the stack is going to start growing. And the first thing that goes onto the stack, we've got some frames and things below us. The first thing that goes on the stack is we see a push long, and again the L is saying long, which is a 32-bit quantity. So I'm pushing 32-bit quantity that's in the EBP register. Notice the use of percent here. Percent just indicates that what follows is a register as opposed to a label name. So you'll see the register names preceded by a percent sign when you're using a Linux assembler. So what happens is the stack, again, is growing this way. So I'm talking about the stack here. I'm going to try to keep track of what the stack does as the program executes. What you see here is you get the old EBP pushed onto the stack. That's what the push long instruction does. The push long instruction, again, puts a 32-bit word on top of the stack and moves the stack pointer to a lower address in order to extend the stack, because the stack is growing from high down to low. And the next instruction then sets up the EBP register to now point to that word, right? It moves the ESP register into the EBP register. So the pointer to the top of the stack is moved to also point into the EBP, because remember, the old EBP points down further down in the stack, and we just established a new EBP to point to the saved old EBP. Okay. Again, when you look at the Intel manual for a move instruction, you'll see these operands reverse. This is what I want to warn you about. The Intel manuals are assuming a different assembler, not the Linux assembler. And unfortunately, the other assemblers have the operands reversed. Okay. So that's boilerplate code. Again, you'll see all of this sort of stuff at the top of all functions, basically. Or this is the function name. That circled item is the function name, because all good Intel functions are going to save the frame pointer and establish a new frame pointer. Now we're entering the code for the function body, and what it does is it does a push long of $10. $10 indicates that what follows is an immediate constant, so the 10 will actually be packed inside the instruction. If you leave the $sign off, you would be talking about address 10. So again, sort of a common error when you're programming in Linux assembler. You might forget the $sign. But in this case, the $sign indicates it's in a constant here. So I'm pushing 10 on top of the stack. Okay. That's the argument, because that function, in fact, the comment tells us it's computing factorial of 10. That 10 is just hard-coded into the program as a constant. Next thing is you see a call instruction. Call the function at address fact, where the label is called fact. Okay. Well, the call instruction, what it does is it saves the EIP, which would have been updated by the fetch execute cycle to actually point to the next instruction after the call instruction. And that's the return address. Okay. So we're remembering where we want to return to back in main as we go off and call factorial. Okay. So let's go ahead and jump into the factorial code, and then we'll come back and look at the rest of main in a minute. So I'm going to swap out this page, bring in the factorial function down here. Okay. So again, we see some comments, and we see this boilerplate code. All right, where this function is named factorial. It was being called by the call instruction in main. So when factorial is entered, it's going to push the EBP. So this is the old EBP. I should have written, well, I won't change, but this is the return address. It's the old EIP once we're up and running inside of factorial. The old EBP, however, that I just pushed here is going to point down here, right? You can see this chain, again, this linked list, if you will, of all the frames. And then it's going to establish a new frame pointer here. So this will be changed to point to the new frame. We're establishing a new frame now for the factorial function itself. Okay, so that's boilerplate code like all good Intel functions do. Now we come into the body of the factorial function. It checks for the base case of the recursion. This is a recursive implementation of factorial. So it checks. It's a compare long. Again, you sort of break these into two parts, right? You get compare of long. Comparing a 32-bit quantity. What am I comparing? I'm comparing the constant 0. The dollar sign again indicates an immediate mode constant. Right, the value 0 to 8 off the frame pointer. So what's 8 off the frame pointer? Again, 8 off the frame pointer is, this is 0 off the frame pointer, 4 off the frame pointer, 8 off the frame pointer is the argument being passed, the single argument. So it's checking to see if the argument passed in is in fact the base case of the recursion, value 0. The way the compare long instruction works is it does the comparison, then it actually side effects. It uses a register called E flags. I think of it as condition codes. It remembers the result of the comparison in this E flags register inside the CPU. And the next instruction is a jump greater than, which checks E flags to see what the last instruction placed with respect to the greater than condition. And if it is greater than, in other words, the base case of the recursion is not present, we jump to label L2. So this is a jump greater than to L2. So if the value compared was greater than, then we're jumping off to L2. Okay. If it was not greater than, though, then it's a move long of $1 into EAX. Remember, EAX is the return register. Okay. And then I would jump down here to L1, which is the return sequence for the function. So if it is the base case, I would have just loaded 1 into the EAX register, and I would jump down here and return. And we'll talk about that code a little bit more in a minute. Let's look at the recursive case, though. The recursive case is come through here. Right? What do? I move along the argument 8 off the frame pointer into the EAX register. So I load n into EAX, essentially, where n is the argument. I subtract 1 from it. Okay, and then I push EAX. So we look here at our diagram. At this point, I would be pushing 9. And I call factorial again. Again, the call factorial is going to put the EIP register there. And then we'll re-enter this function again. This function would then save the frame pointer and establish a new frame pointer here. We would start executing factorial all over again. Notice again, on the second call to factorial, things are still lined up where the argument, which is now 9, is then 8 off the frame pointer, which is where we expect to find the first argument. Okay. So we would spin through this code, driving the argument down from 9 to 8 to 7 to 6 to 5 to 4 to 3 to 2 to 1, and finally to the base case of 0, right? And the code would start unwinding all the way back. So, we'd have all these frames stacking up here, and then it would start returning, and all the frames would be popped off, and we'd come all the way back down here. So let's imagine we're returning within the function call for argument 9 from factorial. Remember, the answer so far is going to be an EAX. And let's see what happens from that point forward. Right, I'm going to add 4 to the stack pointer. What does that do actually? Well, what I failed to do was I failed to pass the next argument on, right? The function call that was running with f of 9, factorial of 9, would have pushed 8 onto the stack as an argument and then invoked factorial again. So when I come back, I've got to get rid of that argument. It turns out in the Intel world, the convention is that the caller pushes the arguments on, and the caller has to remove the arguments off the stack after the call. So that's what this is doing here. By adding 4 to the stack pointer, I'm moving the stack pointer to point down here. In effect, popping that thing off the top of the stack. Okay, so that's another common error I make when I'm programming in assembly language, is I forget to clean up my arguments. And if you don't clean up the stack, you'll have a seg fault, and we'll see why in just a second. But this code is correct, I believe, and so it pops off the argument. It's essentially like a pop instruction, except I don't want the value anywhere. If I do a pop instruction, I have to pop it into a register. Here, I just want to add to the stack pointer just to ignore that value there. Next step then is an integer multiplied long. So this is integer multiplied long of 8 off the frame pointer. In this case, that's the 9 times EAX register. The contents of EAX register is equal right now to factorial of 8. So I'm computing 9 times factorial of 8. In other words, I'm computing factorial of 9. Okay, and the answer ends up in the EAX register. So this is a multiply of this value to that register. And the answer ends up in that register. Just like this is a subtraction of 1 from that register. Right after doing the multiply, then I fall into the boilerplate code for returning from a function. And what happens when I return from a function? Well, I do a pop long to reset the EBP register. So I do a pop long at the top of stack into EBP. This reestablishes, this gets rid of this one, reestablishes EBP to point here. And then I do a return. What the return instruction does is just pop the top of stack into the program counter, into the instruction pointer. So this is what actually causes control flow to then return back to the next instruction after the call. So the stack at this point, I guess I'm making a big mess here, but the stack at this point is, the ESP is now pointing here, right? The return instruction does a pop of the top of stack into the EIP, the program counter. And that puts me again back. This is a recursive situation, so again I'm back at this line, after the return of f of 9. And this is again where I see that I'm popping off the 9. So I get rid of the 9 off the top of the stack. I multiply, which picks up the 10 and multiplies it by EAX, which is factorial of 9, puts that back in EAX. Okay, and then I fall out into the pop long instruction. The pop long instruction is going to get rid of this, and it's going to make EBP point down here again. And then the return instruction is going to pop off the EIP, leaving 10 still on top of the stack. Okay, at this point I'm returning back to main now. Okay, so I got to go back to the other code. I'm back executing in main. I've got 10 on top of the stack. My frame pointer points here. And what is the instruction pointer now? Well, it's right after the call to fact. Right, so it is going to point at this instruction, the instruction right after the call to factorial. And again, you'll see the next instruction is to add 4 to the stack pointer. Again, adding 4 to the stack pointer gets rid of the 10 off the top of the stack. Then I see a push of EAX. Again, remember, EAX is the factorial of 10. It's the computed value. And so I push onto the stack, and I guess I'm going to have to, not sure how to draw this. I'll draw it to the side. This is where a whiteboard would have worked better, perhaps. But I'm pushing, really, the value of factorial of 10 on top of the stack, which is right above the saved frame pointer. Then I push something, $, this label down here. When you see the $, in front of a label, what you're talking about is the address of that label. And what I'm doing is I'm pushing the address of a string in order to set up a call to printf, right, in order to print this value. So I get the address of a string, right? Address of a format string. Format string. I'm having a hard time writing. Apologize for that. But it's this format string over here. I'm putting its address on top of the stack. Again, notice that string was placed down below a .data directive, so it was placed into a data segment of the program. The .string is just a directive that says, please put the ASCII code for this string. And null terminated, I think, into memory, and I give it a name, a label, so I can refer to it. And I'm just referring. Again, the $sign here, a little bit tricky. $sign says I'm not referring to the word at that address. I'm referring to the address itself. Okay, because again, I'm setting up, I'm implementing an assembly language, a printf call that written in C would be something like this, right? That factorial of 10 is %d/n, and then I've got, as the second parameter to printf, I've got the return value of factorial of 10. So it's as if I wrote that in C. I'm going to get this code either generated by a C compiler or written by hand, in this case by myself. Okay, but I'm calling printf. So again, I'm going to have an EIP here. Printf is then going to be entered, and the stack is going to come and grow as printf does its thing. It probably calls some helper functions to get its job done. So the stack frames will go on and come off. Eventually, though, printf will put stuff in the output buffer and return back to me. And now you'll note that my code has to return 8 things, because the saved instruction pointer would have been popped by the return instructions from printf, leaving the 2 arguments still on the stack when it gets back into my code. So now I've got to add 8 to the stack pointer in order to pop off those 2 arguments. And now we enter the boilerplate code for exiting a function, which is to pop the frame pointer and do a return. So what this tells you is that underneath here there must have been a saved EIP register from the stub of code that calls the main and the way Unix starts up processes. This actually returns us back to that stub, which then shuts down the process. Okay. So I'm hoping that code illustrates the basic features of the Intel assembly language and the software conventions for how functions are supported. Remember, the main goals when you look at this video and you think about it, you want to make sure that you understand these main goals. You know, how the hardware and the software conventions support recursive function calls, how return addresses are handled, how return values are handled, how parameters are handled, where local variables appear, because those are going to be important to us when we later in the course we think about writing a garbage collector or implementing a threads library. Okay, let me stop here.